So welcome back everyone, and let's look further on here at what we've begun to discover about optics. So we found that this biconvex lens, this effectively continuously varying triangular prism, will produce an image. And now, as you can understand from just basic logic, this could be shaped somewhat differently and create distorted images and so on. But we're going to stick with a spherical lens that is what we call thin. So that means is that this distance here is small compared to this distance here, okay? And the focus therefore is comparatively long. Now the reason we do this is because we want to keep the mathematics simple. When you get into more distortions, you have to the simplifications that we're making with respect to our similar triangles and so on fall apart, and you have to deal with more complicated issues. I should add, of course, further that this is two-dimensional here, but real lenses are three-dimensional, and then the requirement to determine these bends requires calculus. So this is why we generally don't move in optical study much beyond what we're doing here in this course in high school, because the math very quickly requires advanced techniques. But we can still learn a fair bit in our quasi-simplified universe. So once again, we have, this is the convergence point that we saw yesterday and the last time, the convergence of rays. Now notice I have it on both sides, because clearly the light could come from this side and form an image here, or we could have light on this side, form an image here. So there is a symmetry here that's, makes sense. The observer would be on one side and the object would be on the other, and so forth for most cases. We have the point at the center of the lens called the optical center. We have, of course, like the focus, and twice the distance from the focus is 2f, and this is in both cases. And the line down the center here is known as the principal axis. Now what we're going to find is that if the object is beyond 2f, in between, or inside, we get images that have different character, and we're going to have to think about that a little bit. But to do so, we have to come up with some basic ray tracing guidelines. One, a ray through the optical center is not refracted. Now you might say, well, how do we know that? Well, if you think about it, if you run a ray, this is really just going through a horizontal block at this point here. And these prisms here are very close to parallel. So because we have a thin lens, we're going to get a trivial amount of image shift, which we're going to ignore. An incident ray parallel to the principal axis is refracted through the opposite focus. Now that's, and of course this goes backward, converse, so 3, so 2 works in reverse. So if we have a ray that's somehow coming from another place through the focus, it'll be refracted parallel to the principal axis. Okay? And that's pretty much it. We don't have to think a lot farther than that. So let's rub some stuff out here and make some basic diagrams and see if we can understand what's going on. So the first case we'll have here is where the object is beyond 2F. So we'll take our axis, we'll just make the lens aligned, keep it simple here. We have our foci on either side, make things a bit longer. Here's 2F and F. And so we're going to put our object right here. And so let's trace out these rays and see what we get. So once again, how do we know where the image forms? When the rays from this point all come to a point at the same point in the image, that's where the image is going to be. If it's not there, then the image will be smeared. So I'll show you what I mean again. We've talked about it already, but let's just do it again. So here's this parallel ray here. It hits the lens and it goes through the focus. But here is a ray that goes through the optical center and crosses here. And now we have a point where two rays from the tip of the arrow go about their business, go through this lens, and at this point they recombine. At this instant, in this location, and nowhere else, all the information from this point is returned here. Now, you can take other points down the arrow and you will get corresponding points down the image. We generally don't draw them because it makes the diagram complicated. We could there would be, of course, other rays. We could have, for example, a ray from here that would also work. Let's do this one. We could do this too. A ray could come from here through the focus, hit the lens, and will be refracted parallel. So those are three rays that go where they're supposed to go, so to speak, based on the guidelines in the previous panel. Notice, and I didn't draw it yet, but we have our focus point would be here. This is F. 2F's about here. So this image is inverted. And it's actually smaller. It's harder to see. You can, of course, do all these things to scale with circles and so on. It's projectable, so it's real. And it's between F and 2F. One of the nice things about this situation is that these are reciprocal. So situation of item 1 is reversed. For an object located between 2F and F. We can see this here. Here's our object here, and its image then will be beyond 2F. So we can, without even having to draw the diagram, we'll see once again that the image is inverted in the sense that it's opposite in orientation to the object. It's larger, the reverse. It's real, of course. And now it's beyond uh, 2f. We might see what might the applications be. Well, this could be a camera lens. Or, and of course there's more complexity to telescopes, but let's use that one. This could be a projection lens. And we could set this up, if we're careful, that this distance is quite a ways off, and that would make this much bigger. So this would be the example of a projector. Let's look at, for the final one on this panel, let's look at the case where the object is right at the focus. It's amazing, but maybe you haven't studied optics before, but you actually already know what's going to happen here. You've probably had this experience. So here's the object. So we'll do the same old story here. The ray comes through, and we'll go through F and keep on going. We have another ray that will come through the optical center, but what we find, these rays are parallel. And because the rays from this point never can return together, no image is formed. Now you've experienced this. If you take a magnifying glass, a standard magnifying glass, which is basically the lens we're looking at here, and you are holding it, looking at a postage stamp or something, and you back away. If you back away a long way, everything looks smaller and looks upside down. And then you come in, and there's a change, and suddenly, at a certain point, the whole thing goes just completely blurred, and then suddenly you see this magnification effect. And this blurred situation is when no image is formed. And that's because you're basically at the focal length of the lens. Now we have to be a little careful about the assumptions we make, because remember, our eyes have two lenses, the cornea and the lens itself. And so what we're seeing, of course, is an image in our eye that's created also on top of whatever else these lenses might be doing. So we have to be a little careful. But we're still, in one way or another, encountering this transition. Alright, let's clear the panel here, and we'll do one more. Now let's take a look at this case, which is more confusing for most students. The object is here, which is between F and the lens, and I drew the lens again just to show it a bit more effectively in detail. We take the rays, the three rays from the tip of this arrow that we know already. One ray would go through the lens and keep on going. Another would go parallel to the principal axis, would be refracted through the focus. Another one would go through the optical center. Now if you stand on this side, you're not going to see anything, because the light that is, well, that, I should say, that's a silly thing to say. If I stand on this side, okay, what am I seeing here? I'm seeing three rays that are diverging. Now, you have to understand that the eye does not understand that the lens bends the light. We do not see this bend in the path. Okay? We don't notice that. All it does by doing so is to make an object look bigger or smaller or whatever. However, in this case, the image, because these are diverging, there is no projection image on this side. There's no projectable image. The image then appears behind and is seen by an observer. So we'll draw the eye, if you will, of the observer here, looking backwards towards this. And now what happens is, and this is where we have, it's a little harder, is you can take these three rays, which we've already used, and extrapolate them backwards from assuming no refraction at all, okay? And they will converge right here, and this produces a virtual image that is larger. This is, of course, your magnifying glass. So this particular one, so if the object then is inside F, then we get an erect image. It is larger. It is also inside F. And the image type here is virtual. So that's a bit of a different situation, but you do see the magnification. I'm going to show you another one in a few minutes where we also get the optical effects of these extrapolations, so to speak. But let's do one more lens. And this is an opposite case where we use the same geometry. Only we make it what we call concave. The other was a convex lens. We still have F and 2F. And the image is now formed almost the reverse of this one. Okay, so if we have an object sitting here somewhere, let's suppose, what happens with these rays is they behave the opposite. So if we have, for example, a ray parallel here like this, it will be diverged, and such that this divergence would go through the focus. We would have still this situation, would not change. And so let's see if we can divine, and we can already see it here. If we extrapolate this ray, you will see that we get a very small image here. Now, this particular lens, this diverging lens, it's also known as a Barlow lens. And once again, we have a virtual image. It's smaller. It's inside F. And the image is erect. Now you might say to me, well, this is a very strange thing. I mean, I understand magnifying glass. That makes perfect sense. But my gosh, who would ever want to use something like this? You may be surprised. Okay. Now we'll leave this as a little bit of suspense here. But we'll look at that too. Let's look at a different example entirely. Something you may well have seen as a child when you've gone swimming or something. We have a pool. Actually, I'm going to redraw that a little bit different. And because we're Canadian, we have a hockey puck sitting on the bottom of the pool. And what you're going to find and what you notice is the hockey puck does not appear as deep as we know the pool to be. So you're up here looking down at the pool, the observer's eye, and let's see what happens. So rays from the puck will come up almost vertically, but we're coming from a slow medium to a fast one, so they diverge a little bit. This is enhanced, of course, just to show it to you. And what you don't know that, so then what you see is this. This is where the hockey puck forms for the observer. Now this is enhanced, it's not that obvious. And the same thing happens, for example, in the islands where spearfishing occurs. If you can see it here, that the puck, if you were, let's just draw it on the same map here, we have our fish. And the rays from the fish, you know, come up like this and are bent this way to our fisherman, which we'll draw yet again another eye here. And if they were to throw the spear where the fish appears to be, the spear will miss over top of the fish and they'll starve. So these people learn quickly when they're training as children that when you see the fish, you aim below it, because the optical effects of the surface are fooling you. Let's look at some other basic phenomena too that happen. You might say, if you are, it's a little bit difficult when you're swimming because of the way the water goes up your nose and so on, but if you were able to lie, go underwater and look back up at the surface, it's an interesting effect because, and this is to be when the water's calm. If the water is turbulent, then of course the lens, if you will, is being radically distorted. But if you can look upward on it is an effect of magnification. Okay, you're going to see the sky closer. It's going to give you a bit of a prescription. Some of you may notice, if you're myopic, when you go swimming, if you open your eyes underwater, that you see a little better. It'll depend on your prescription. But you have a cornea-water relationship versus a cornea-air relationship. And so the effect of how the light rays are bent is different, not as dramatic. So it's kind of interesting how these things look. Another thing we can talk about is examples of just these types of basic technologies would be on a car. You have a window, and when it's raining, the view of the road is blurred. And so we have a safety device called a windshield wiper. It removes the water. But let's look at why this is necessary. Water's a fluid, it's just going to run off your window anyway. What's the point? In most vehicles, the windshield has sufficient slant to it and you're not going fast enough that the water forms little balls, little beads, like so. And this is, so these water beads, or whatever you want to call them, is due to something called surface tension. And this is a tendency for water and other liquids to cling to things. And when they do, they tend to form these spherical round balls. This is a property of these materials, and this of course is one of the reasons, say for example, why certain insects can walk across water and so on. And it's just one of these properties. But what it does in our case is that these things form random lenses. And when they do that, of course, they distort in real time our view of the road. Now the wiper removes the bulk of the water and then the lens effect is vastly reduced. So it is interesting that we study these things, but lenses of different kinds form naturally in nature and can be useful or otherwise. Sometimes the water droplets form on plant leaves form a lens which causes the sun to burn a hole in the leaf. It'll just depend on the accident of the angle of the leaf and how big the drop is and all the rest, as to whether this happens before the water evaporates in general. So it's quite interesting, I think, how these things work. Okay, so let's look at this situation. If we have our equation we had before, high over ho equals negative di over do, it works fine. The problem is that the height of the images are values that are difficult sometimes to measure. And so we would want to try to rearrange our algebra if we can, so that we can get away from having those variables in our actual equation. Well, let's look at a typical lens situation. We have the object at 2 plus 2f here, and the image therefore between f and 2f. And we're going to mainly deal with these two triangles here. So we've got the ray coming to the lens, refracting through the focus and continuing on, and we have the image here. We could argue that these two triangles are similar. We have a opposite angle here, and because this is vertical and the lens is erect, we have this angle and this angle here are also equal due to transversal parallel line theorem. This is also 90 and this is also 90. So one way or the other, these two triangles are similar. This puts them into a particular ratio. So we have the height and the height of the object ratios, and we have the ratios of the length, and this is where it gets interesting. So what we're going to have in this particular case is we'll write again once again high over ho equals. Now once again this is inverted to this one, so the sign must switch. So we're going to say negative, and this distance from the focus to the image is simply di minus f, where this is the distance from the optical center to the focus, called the focal length, you may have heard before. So we'll have di minus f here, divided by, and then the distance from here to here, of course, is simply f. Okay, now, but we also know that high over ho is equal to negative di over do. And this is the substitution that we now make. So negative di over do equals negative di minus f over f. So we could write it that way. And we just want to be careful changing these signs too much and getting too clever. We certainly can multiply through here and get one where we would have f minus di. That one's fine. So let's cross multiply and see what we get here. So we're going to get minus di f equals dou f minus dou di. No, that's right. Oh, sorry, yes, dou f. Here we go. There we go. So now we want to combine these two. So we'd end up with something like this. Dou di is equal to dou f plus, I'm sorry, this would be plus here too, di f. So get rid of the negatives, move things around. And then we can, once again, take f, dou plus di is equal to dou di. And we would have f equals dou di divided by dou plus di. However, you may notice the pattern here, and we can write, and we tend to write it this way instead. Now this is known as the lens maker's equation. Or the thin lens, something like that. Okay, and it's used. And so what's nice about this is that the image sizes, which still can be computed from up here, are now determined by how far you are away from something, and the distance of the image. Oftentimes, if you have a camera or something, it's going to be fixed, or pretty close to it. You're not going to have much difference in distance. So this does constrain things and make it a bit easier. But remember also, when we focus our camera, such as we turn a ring or something, we're literally moving the lens. So that adjusts this distance of the image somewhat as a function of focal length. And this, of course, then would be sensitive to the distance of the image. And this is why you focus a camera. So hopefully that gives you that perspective on all of this. It's quite amazing, actually. So we should discuss briefly some issues with lenses. The first one is what we call chromatic aberration. And this is simply that the index of refraction is truly a function of the wavelength. And so what you get if you have a lens like so is that down here the blues and the reds, to take the opposite ends of the spectrum, are, so your reds are fairly long, the blues get refracted more aggressively, like so. So your object, if you focus, so we generally, humans, focus to yellow-green. That's the area of our eye that's most sensitive. It's because it's the same as the sun. And so we have our object, okay, and what you find around it is a purple haze. So you get a because where it is in focus for the yellow-green, if you see arbitrarily here, okay, then the reds and the blues will both be out of focus slightly. The distances are obviously much smaller than I'm drawing on this, just for representation purposes. And now this is, recreationally, is irrelevant. So recreationally, a nuisance, if anything. But scientifically, it's unacceptable. Because we take spectra, observations are impaired. And we can't have that. So if we do this type of work, we have to correct it with extra optics. So the correction is subsequent lenses which attempt to cancel this out. So with take a telescope, for example, you have your first lens, say. You might have 2 or 3 other lenses that are part of it, that might be right behind it, like this. So this is what we call a doublet. And this can be, it's a different shape, and it may well be different glass. Now the smart people figure out how to do this, okay? But this is the challenge that we have here with the with this type of work, and this can be true. It doesn't have to just be telescopes. You can have objects, even in medicine. If a surgeon is looking through optics to operate on someone, they cannot have blurs or ghost images or whatever. And this is why you have to pay, okay? So for this type of stuff, you're looking at a lot of money. So you might go somewhere and buy a set of binoculars or a telescope or something, and for maybe a few $100s, and think you've done well. When the scientific standard might be 10 or even 50 times more expensive or more. Depending on the circumstance and what is being asked of it and the obligations. Remember also, as we'll talk about in grade 11 physics, when we deal with uncertainties, and you see this even with the COVID crisis, and again, the challenge of the COVID crisis is to know what the uncertainties are, so that's a different discussion. But if we know what the uncertainties are, then we have to look at the consequences. Because if the consequence is catastrophic, massive personal injury, death, massive economic consequence, etc., then it can't happen. We have to do everything realistically possible to prevent it. If we look at, and our mindsets are different about these things. So for example, a car is still a very well-made piece of machinery. We expect our cars to, for the most part, work every time we get in them and drive away. We don't expect our car to break 1 day out of 10. If it did, we would consider it a lemon. But if you think about what's being asked of the car to work under those conditions with comparatively minimal maintenance, and even though the operating manual of the car has standards of what you're supposed to do, most people don't bother until it actually breaks. But if the car does break, what happens? Well, it slows down and pulls over on the side of the road. Generally speaking, stops working. But you're on the ground. So the biggest real hassle is the inconvenience. You have to phone for assistance, the car is towed, you have to pay a repair bill, wherever you were going, you have to make adjustments. It's a frustrating day because this car for once has let you down. But if we're flying on a jetliner and something fails and the aircraft can't continue, then we have catastrophe, not only in the air with the people on board, but also on the ground. And so from a human standpoint, we don't want that. We think that's unacceptable. And so the standards for aircraft maintenance and production and all the rest are vastly higher than they are for cars. And it's also a business issue too, because if you think about it from the airplane standpoint, the airlines, killing your customers is bad for business. So they don't want anything to go wrong either. So they're quite willing to support these things. And so this is why you pay a lot of money, a lot more money than the average person might think you need to pay for some of these devices if they are working in highly dependent areas such as medicine, or you're trying to get very, very precise scientific measurements, and whomever the government and so forth has decided that those are valuable. So then the money is spent to get a device such as the Hubble Space Telescope that is so precise and so well crafted. They say that if the Hubble Space Telescope's mirror was the size of the United States, that the biggest bump on it would be no more than 10 centimeters. Now, that's a truly incredible accomplishment. But you pay for that, okay? And that's what billions of dollars buys you. Okay, we're going to move on in this study, but this is the story of simple lenses, and thank you for watching.